I'm going to use LabVIEW to explore the time delay through the all-pass filter. I'm beginning with the math script node, and I will define my frequency range using the linspace function. Linspace is an abbreviation for linearly spaced points, and I'm getting an array of linearly spaced points between 0 and pi. My frequency response is the filter's transfer function evaluated at e to the j omega. Any place that I see as z, I change that out for e to the j omega. After I'm done writing my numerator, I also make sure to do dot divide since I have a vector on top, and when I'm dividing by another vector, I'm trying to do vector-oriented division, that is sample by sample division. I'm not trying to imply a matrix inversion, which is what will happen if you just use the divide by itself. I'll add some inputs and outputs since the filter coefficient C is one of my input parameters I want to explore. Remember to choose complex value for H since the filter response is a complex valued function. Here I can retrieve either the magnitude or the phase as needed. I'll use the XY graph, and the XY graph requires a cluster of two arrays. One array would be my independent variable, which is frequency, and the other is my dependent variable. And I'll start out by plotting the magnitude. And I can put in some values for my all-pass filter coefficient C. C is going to range between 0 and 1, so I'll put in a midpoint value for now. It looks a little ratty, but if you notice that this is an extreme zoom, if I change my display range from 0 to 1, then we see that it's a flat line response over all frequency. That confirms that we have the correct all-pass filter equation entered since we have that unit response across all frequency. Now I'm switching over to the phase response. I'd like to be able to simply work the front panel control for C and then have the graph update right away. So I'm wrapping the whole thing in a while loop. And then, so it doesn't evaluate so fast, I'm going to put down the wait until the next millisecond multiple. And this makes the loop update 4 times a second. That is once every 250 milliseconds. C is only supposed to range between 0 and 1. So, I guess general observations here, we see that the phase response certainly is not linear, so that means it does not have a uniform time delay across all frequency. However, it does have a fairly linear response through the approximately the folding frequency, or half of the sampling frequency. And for our purposes, that will be sufficient for establishing a variable time delay. Since time delay is negated slope, I'm introducing a negation in here just to make it a little bit easier to concentrate on. And again, if you think about the slope here, this would correspond to a higher time delay. And as I increase my value of C, I have a smaller slope, so that means I have less time delay. So C gives us a great knob, so to speak, to get a continuously adjustable time delay.